Imagine standing at a moment in history when scientists were surrounded by unanswered questions, questions so simple in appearance, yet so profound in meaning. One of those questions was this: what truly connects electricity and magnetism? People had already observed sparks, currents, and magnetic needles responding to wires, but the deeper relationship remained unclear. There was a mystery hidden in plain sight, and it revolved around one powerful idea: the behavior of moving electric charge. At first, electricity and magnetism seemed like separate phenomena. Electricity was associated with charges, sparks, and currents flowing through wires. Magnetism, on the other hand, was linked to magnets, compasses, and invisible fields that could pull or push objects without contact. Scientists knew these forces existed, but they didn't fully understand how tightly they were connected. It was like having two pieces of a puzzle without realizing they were part of the same picture. The turning point began when experiments showed that an electric current flowing through a wire could deflect a nearby compass needle. This suggested that electricity in motion had something to do with magnetism, but this discovery opened up even more questions. Was it only electric current in wires that created magnetic effects, or was there a deeper, more universal principle at work? To understand the mystery, we need to think about what an electric current really is. At its core, a current is simply a flow of electric charges, usually electrons, moving through a conductor. If moving charges create magnetism, then perhaps magnetism is not a separate force at all, but a natural consequence of motion. This idea sounds simple today, but at the time it was revolutionary. Scientists began to suspect that motion itself might be the key. Not just any motion, but the motion of electric charge. If a charge sits still, it creates an electric field. But if that same charge moves, could it also create a magnetic field? This question became one of the most important puzzles in physics. The challenge was not just to think about this idea, but to prove it. Science demands evidence, not just imagination. And the difficulty was enormous. The effects of moving charges can be incredibly small, especially when the motion is not part of a strong current. Detecting such tiny magnetic fields required precision beyond what most experiments of the time could achieve. This is where the story becomes fascinating. Scientists were not just exploring ideas. They were pushing the limits of measurement itself. They needed instruments sensitive enough to detect forces that were nearly invisible. They needed to eliminate errors, reduce noise, and ensure that what they observed was real and not an illusion. The mystery of moving charge and magnetism was not just about discovering a new fact. It was about changing how we understand forces in nature. It challenged the idea that electricity and magnetism were separate. It suggested that they might be different expressions of the same underlying phenomenon. To appreciate this, imagine a single electric charge. When it is at rest, it produces an electric field that spreads out in space. This field can push or pull other charges, but when that same charge begins to move, something new appears: a magnetic field. This magnetic field does not replace the electric field, it exists alongside it. Together, they form a more complete picture of reality. This dual nature of electric charge, producing electric effects when still and magnetic effects when moving, was a profound insight. It meant that motion changes the way forces behave. It also meant that observers might see different effects depending on how they are moving relative to the charge. This idea would later become even more important with the development of modern physics. But at this stage, scientists were still trying to confirm the basics. They needed to answer a simple but deep question: Is magnetism always linked to moving charge, or are there exceptions? The answer would reshape physics. If magnetism always comes from moving charge, then permanent magnets themselves must involve motion at a microscopic level. Even though a magnet looks still, the charges inside it must be moving in some way. This idea connects the visible world to the invisible world of atoms and electrons. The mystery also pushed scientists to think more carefully about fields. Fields are not objects you can touch or see directly, yet they are real. They carry energy and influence matter. Understanding how electric and magnetic fields are related became one of the central goals of physics. One of the greatest contributions to this understanding came from James Clerk Maxwell. He developed a set of equations that described how electric and magnetic fields interact. His work suggested that changing electric fields could create magnetic fields, and changing magnetic fields could create electric fields. This interplay hinted at a deep unity between the two forces. Maxwell's ideas were powerful, but they needed experimental support. Theoretical predictions are only as strong as the evidence behind them. Scientists needed experiments that could directly show the connection between motion and magnetism. This is what made the mystery so exciting. It was not just about understanding a concept. It was about proving it in a way that left no doubt. The challenge required creativity, precision, and persistence. Think about how bold this idea was at the time. It suggested that something as simple as motion could give rise to a fundamental force. It blurred the line between different areas of physics. It hinted that the universe might be more unified than previously thought. The implications went far beyond the laboratory. If moving charges create magnetism, then every electrical device, every current, and every circuit becomes a source of magnetic effects. This realization would later lead to the development of motors, generators, and countless technologies that shape our modern world. But at this stage, the focus was still on the mystery itself. Scientists were trying to see what could not easily be seen. They were trying to measure what was almost too small to detect. They were trying to connect ideas that seemed separate into a single, coherent understanding. The beauty of this mystery lies in its simplicity. It starts with a basic question about motion and charge. Yet it leads to a deeper understanding of the forces that govern the universe. It shows how even the smallest details can have enormous significance. As the investigation continued, one thing became clear. The answer would not come from theory alone. It would require an experiment that could isolate the effect of moving charge and measure its magnetic influence directly. Such an experiment would need to be carefully designed to avoid confusion with other sources of magnetism. This is where the stage was set for a breakthrough. The mystery had been defined. The question was clear. The tools were ready. All that remained was to find a way to demonstrate the truth beyond doubt. The journey toward that proof was not just about solving a problem. It was about expanding the boundaries of human knowledge. It was about showing that the universe operates according to principles that can be discovered, understood, and tested. And perhaps most importantly, it was about revealing a hidden connection, one that links motion, charge, and magnetism into a single, elegant framework. A connection that reminds us that nature is not a collection of separate pieces, but a unified whole. This mystery, once solved, would change everything. It would transform our understanding of physics. It would open the door to new technologies, and it would show that even the simplest questions can lead to the most profound discoveries. The story does not end here. In fact, this is only the beginning. The mystery of moving charge and magnetism would soon be explored in ways that no one had imagined. And the answers that followed would not only confirm the connection, they would redefine the very nature of physical reality. As scientists moved deeper into this question, the mystery began to shift from a simple curiosity into a serious scientific challenge. It was no longer enough to say that electricity and magnetism were somehow related. The real task was to understand how and why this relationship existed in every situation, not just in obvious cases like wires carrying current. One of the biggest difficulties came from the idea of motion itself. When we say a charge is moving, we must always ask, moving relative to what? Motion is not absolute. It depends on the observer. This raised a subtle but powerful question. If magnetism is created by moving charges, then would different observers see different magnetic effects depending on their motion? This idea pushed scientists to think more carefully than ever before. To explore this, imagine a single charged particle. If you stand still and observe it at rest, you will detect only an electric field around it. There is no magnetism in your frame of reference. But now imagine that you start moving past that same charge. From your perspective, the charge is now in motion. According to the emerging ideas of physics, that motion should create a magnetic effect. This leads to a surprising conclusion. Magnetism is not just about the charge itself, but also about the relative motion between the charge and the observer. What appears purely electric in one situation can appear partly magnetic in another. This realization was not only fascinating, it was deeply unsettling because it challenged the traditional idea that forces are fixed and absolute. At this stage, scientists began to see that electricity and magnetism were not separate forces at all, single, unified phenomenon. This unified view is now known as electromagnetism. It describes how electric and magnetic fields are intertwined, constantly influencing each other in ways that depend on motion and change. The deeper they explored, the more they realized that magnetic effects always seemed to trace back to moving charges. Even in materials that appeared to be permanent magnets, the explanation pointed toward motion at a microscopic level. Inside atoms, electrons move in complex ways, creating tiny loops of current. These microscopic motions combine to produce the magnetic fields we observe on a larger scale. This idea brought a new level of unity to physics. It suggested that all magnetism, no matter how it appears, is ultimately rooted in the movement of electric charge. There are no exceptions, only different forms of the same underlying principle. However, understanding this in theory was one thing. Demonstrating it clearly in an experiment was something else entirely. The effects involved were often extremely small, especially when dealing with static charges set into motion without forming a conventional current. Detecting such subtle magnetic influences required not only advanced instruments, but also extraordinary care in experimental design. Scientists had to consider every possible source of error: external magnetic fields, vibrations, temperature changes. Any of these could interfere with the measurements. The challenge was to isolate the effect of moving charge so completely that no alternative explanation could remain. This demand for precision changed the way experiments were conducted. It was no longer enough to observe general trends. Scientists needed exact measurements, repeatable results, and clear evidence that could withstand scrutiny. The pursuit of this mystery helped raise the standards of experimental physics to a new level. At the same time, the theoretical framework continued to evolve. The work of James Clerk Maxwell played a crucial role in shaping the understanding of these phenomena. His equations described how electric and magnetic fields are generated and how they interact. They showed that a changing electric field could produce a magnetic field, and a changing magnetic field could produce an electric field. This interplay suggested something even more profound, that light itself is an electromagnetic wave. In other words, the same principles governing moving charges and magnetic effects also explain how light travels through space. This was a breathtaking insight, connecting everyday electrical phenomena to the behavior of the universe on a cosmic scale. But even with such powerful theory, the need for direct experimental confirmation remained. Scientists wanted to see, in a clear and undeniable way, that motion alone could give rise to magnetism. They wanted to remove all ambiguity and show that the connection was not just a theoretical prediction, but a physical reality. The mystery also forced scientists to rethink their intuition. In everyday life, motion does not seem to create forces in such a direct way. We are used to thinking of motion as something that changes position, not something that generates entirely new effects like magnetism. Accepting this idea required a shift in perspective. It also highlighted the importance of invisible phenomena. Electric and magnetic fields cannot be seen directly, yet they are essential to understanding how the world works. The ability to detect and measure these fields became one of the most important skills in physics. As the investigation continued, the question became sharper and more focused. It was no longer just about whether moving charges create magnetism. It was about proving that this principle holds in every case, even under the most controlled and unusual conditions. This set the stage for experiments that would isolate motion in its purest form. Instead of relying on currents flowing through wires, scientists began to think about other ways to move charge. Could a charged object, simply by being set into motion, produce a detectable magnetic field? If so, it would provide direct evidence that motion itself is the key. The significance of this idea cannot be overstated. It would mean that magnetism is not tied to specific materials or configurations, but is a universal property of moving charge. It would confirm that the laws of physics operate consistently across different situations, revealing a deep and elegant order in nature. At the same time, this mystery continued to inspire new questions. If motion creates magnetism, then how do these effects combine when many charges move together? How do electric and magnetic fields influence each other over time? And how do these interactions give rise to the complex behavior we observe in real systems? Each of these questions opened up new areas of research, pushing physics forward in unexpected ways. What began as a simple curiosity about moving charge became a gateway to a much larger understanding of the universe. The pursuit of this mystery also demonstrated the power of persistence in science. Progress did not come instantly. It required years of careful thought, repeated experiments, and constant refinement of ideas. But each step brought scientists closer to a clearer and more complete picture. In the end, the mystery of moving charge and magnetism was not just about solving a single problem. It was about uncovering a fundamental principle that connects motion, force, and energy. It was about revealing the hidden unity behind seemingly different phenomena. And perhaps most importantly, it showed that the universe is governed by laws that can be discovered through observation, reasoning, and experimentation. The connection between motion and magnetism is not obvious at first glance, but once understood, it becomes a powerful tool for explaining and shaping the world around us. This deeper understanding paved the way for the next step, the moment when theory and experiment would come together to provide clear and undeniable proof. A moment when the mystery would finally be resolved, and the relationship between moving charge and magnetism would stand as one of the great achievements of physics. Imagine a quiet laboratory in the late 19th century, filled not with noise and chaos, but with patience, precision, and curiosity. At the center of this scene stands a scientist determined to answer a question that had puzzled the scientific world for years. Can motion alone, without a flowing current in a wire, produce magnetism? This question was no longer just theoretical. It demanded a clear, physical demonstration. That scientist was Henry Augustus Rowland, and the experiment he designed would become one of the most elegant proofs in the history of physics. His goal was simple in concept, but extremely challenging in execution. Take electric charge, set it into motion in a controlled way, and detect whether a magnetic field appears as a result. To understand the brilliance of his approach, we need to think carefully about the problem he was trying to solve. Scientists already knew that electric current in a wire produces a magnetic field, but a current is a continuous flow of charge through a conductor. What Rowland wanted to test was more fundamental: whether any motion of charge, even if it is not part of a conventional current, could generate magnetism. So he asked himself a clever question: what if we take a solid object, place electric charge on it, and then simply make that object move? If the charge moves along with the object, then in principle it should behave like a current, and if that is true, it should produce a magnetic field. This idea led him to design the rotating disk experiment. The setup was conceptually simple, but required extraordinary precision. Rowland used a flat disk made of insulating material, so that electric charge could remain distributed across its surface. He then charged the disk with static electricity, ensuring that the charge was spread as evenly as possible. At this point, the charge was not moving. It simply sat on the surface of the disk, creating an electric field but no magnetic effect. The key step came next. He set the disk into rapid rotation. Now something remarkable happened. As the disk spun, every tiny bit of charge on its surface began to move in a circular path. Even though there was no wire and no traditional current, the motion of charge was real. Each point on the disk traced a circle, effectively creating countless tiny loops of moving charge. In essence, the rotating disk acted like a collection of circular currents, and according to the developing understanding of electromagnetism, such motion should produce a magnetic field. But here's where the real challenge began. The magnetic field generated by this motion was incredibly weak. It was far smaller than the magnetic fields produced by ordinary currents in wires. Detecting it required instruments of exceptional sensitivity and an environment carefully controlled to eliminate interference. Rowland approached this challenge with great skill. He used a highly sensitive device capable of detecting even the faintest magnetic effects. He also took steps to shield the experiment from external magnetic influences, such as the Earth's magnetic field and nearby sources of interference. The experiment demanded not just technical ability, but also deep attention to detail. Even the slightest error could produce misleading results. If the disk was not perfectly balanced, vibrations could affect the measurements. If the charge distribution was uneven, the results might not match theoretical predictions. If external magnetic fields were not properly accounted for, they could mask or mimic the effect he was trying to observe. Despite all these difficulties, Rowland persisted. He carefully repeated the experiment, refined his methods, and improved the accuracy of his measurements. Slowly but surely, a pattern began to emerge. When the disk was stationary, no magnetic field was detected beyond the expected background levels. But when the disk was set into motion, a measurable magnetic effect appeared. This effect was consistent with the idea that moving charge creates magnetism. Even more importantly, the strength and direction of the observed magnetic field matched the predictions based on theory. This agreement between experiment and theory was crucial. It showed that the effect was not accidental or due to some unknown factor. It was exactly what the laws of physics predicted. This result was a powerful confirmation of a fundamental principle. Motion of electric charge produces a magnetic field, regardless of whether that motion occurs in a wire or on the surface of a rotating object. What made this experiment so significant was its clarity. It removed ambiguity and provided direct evidence for a key idea in physics. It showed that magnetism is not limited to special cases like electric currents in conductors. Instead, it arises whenever charges move, no matter how that motion is achieved. The rotating disk experiment also demonstrated the importance of creative thinking in science. Rowland did not simply repeat existing experiments, he found a new way to test a fundamental idea. By using rotation instead of linear current, he was able to isolate the effect of motion in a unique and convincing way. His work also highlighted the role of precision in scientific discovery. Without accurate measurement, the effect he was studying would have remained hidden. The success of the experiment depended not only on the concept, but also on the ability to detect extremely small changes in magnetic fields. Another important aspect of the experiment was its connection to broader theory. The results supported the ideas that had been developed by scientists like James Clerk Maxwell, whose equations described the relationship between electric and magnetic fields. Rowland's findings provided experimental evidence that strengthened these theoretical foundations. The rotating disk was more than just a piece of equipment. It was a bridge between theory and reality. It took an abstract idea about moving charges and turned it into a measurable, observable phenomenon. It showed that the predictions of physics were not just mathematical constructs, but reflections of how the universe actually works. As the experiment gained recognition, it helped shape the direction of future research. It encouraged scientists to explore other ways in which motion and fields interact. It also contributed to the growing understanding that electricity and magnetism are deeply interconnected aspects of a single force. Looking back, it is remarkable how such a simple concept, a spinning charged disk, could reveal such profound truths. The elegance of the experiment lies in its simplicity. It did not rely on complex machinery or elaborate setups. Instead, it used a clear idea, carefully executed, to uncover a fundamental principle. The impact of this work extended far beyond the laboratory. By confirming that moving charges create magnetic fields, it laid the groundwork for technologies that rely on this principle. Electric motors, generators, and many other devices operate based on the same underlying concept demonstrated by Rowland. But at the time, the focus was not on applications. It was on understanding. The rotating disk experiment answered a question that had lingered for years. It provided clarity where there had been uncertainty. It transformed a hypothesis into a proven fact. And perhaps most importantly, it showed the power of experimentation in science. Ideas can guide us, but it is evidence that confirms them. Rowland's work stands as a reminder that even the most subtle effects can be uncovered with the right combination of insight, creativity, and precision. This was only the first half of the story. The full implications of the experiment would continue to unfold, influencing not just physics, but the way we think about motion, forces, and the hidden connections that shape our universe. As the experiment continued to be refined and repeated, its importance grew far beyond a single demonstration. What began as a carefully controlled setup with a rotating charged disk started to influence how scientists thought about measurement, evidence, and the reliability of physical laws. The second phase of understanding was not just about observing a magnetic effect. It was about confirming, validating, and fully trusting what that observation meant. After the initial detection of a magnetic field from the rotating disk, the next challenge was verification. In science, one successful result is never enough. A discovery must be repeatable, consistent, and independent of accidental conditions. Henry Augustus Rowland understood this deeply. He knew that his results would only be accepted if they could withstand careful scrutiny from the scientific community. So, the experiment was repeated under different conditions. The speed of the disk was varied. The amount of charge placed on the disk was adjusted. The sensitivity of the measuring instruments was improved. Each time, the goal was the same: to ensure that the observed magnetic effect was truly caused by the motion of charge and not by any hidden factor. One of the key observations was that the magnetic field depended directly on how fast the disk rotated. When the disk spun faster, the motion of the charges increased, and the magnetic effect became stronger. When the rotation slowed down, the magnetic effect decreased. This relationship was exactly what theory predicted, and it provided strong evidence that the motion itself was responsible. Another important factor was the amount of charge on the disk. When more charge was placed on the surface, the magnetic field increased. When less charge was used, the effect became weaker. This again matched the theoretical expectation that magnetism arises from moving charge. The more charge in motion, the greater the magnetic influence. These patterns were not random. They formed a clear and consistent relationship between motion, charge, and magnetism. This consistency was crucial because it ruled out alternative explanations. If the effect had been caused by some unknown disturbance, it would not have followed such precise and predictable behavior. The experiment also required careful isolation from external influences. Magnetic fields are everywhere, including the natural field of the Earth. Even small disturbances from nearby objects could interfere with the results. Rowland took great care to minimize these effects, ensuring that the magnetic field he measured was truly coming from the rotating disk. This level of control transformed the experiment into something more than a demonstration. It became a standard of precision. It showed how careful design and attention to detail could reveal even the most subtle physical effects. In doing so, it raised the expectations for future experiments in physics. As the results became more widely known, they attracted attention from other scientists. Independent verification began to play an important role. When different researchers, using similar methods, obtained the same results, confidence in the discovery grew stronger. This process of confirmation is a cornerstone of science. It ensures that knowledge is not based on a single observation, but on a body of consistent evidence. The implications of the rotating disk experiment also began to deepen. It was no longer just about proving that moving charge creates magnetism. It was about understanding how this principle fits into the broader framework of electromagnetism. The experiment provided direct support for the theoretical work of James Clerk Maxwell, whose equations described the relationship between electric and magnetic fields. Rowland's findings showed that these equations were not just mathematical ideas, they accurately described real physical behavior. This connection between theory and experiment is one of the most powerful aspects of science. When a theory makes a prediction and an experiment confirms it, the result is a deeper level of understanding. It shows that the laws we use to describe nature are not arbitrary. They reflect the true structure of the physical world. The rotating disk experiment also helped clarify the concept of current. Traditionally, current was thought of as charge flowing through a wire. But Rowland's work showed that current can take other forms. A rotating charged disk does not have charges moving from one place to another in a straight line, yet it still produces a magnetic effect. This means that current is not limited to wires. It is any motion of charge. This broader definition of current opened the door to new ways of thinking about electrical systems. It allowed scientists to explore more complex forms of motion and their magnetic consequences. It also helped unify different areas of physics under a single set of principles. Another important outcome was the realization that magnetism is fundamentally linked to motion at all scales. Whether it is the rotation of a disk, the flow of electrons in a circuit, or the movement of charges within atoms, the same principle applies. This universality is one of the defining features of physical laws. They work everywhere, from the smallest particles to the largest systems. The success of the experiment also demonstrated the importance of indirect observation. The magnetic field produced by the rotating disk could not be seen directly. It had to be inferred from its effects on sensitive instruments. This kind of reasoning, observing consequences to understand causes, is central to much of physics. It also required trust in measurement. The instruments used were capable of detecting extremely small changes, and interpreting these changes correctly was essential. This highlighted the role of technology in scientific progress. As instruments become more precise, they allow us to explore phenomena that were previously beyond our reach. As the scientific community accepted the results, the rotating disk experiment became a key piece of evidence in the growing understanding of electromagnetism. It was cited, discussed, and built upon in further research. It became part of the foundation on which modern physics is constructed. The experiment also had an educational impact. It provided a clear and concrete example of a fundamental principle. Students and researchers alike could study it to understand how abstract ideas are tested and confirmed. It became a model of how to design an experiment that directly addresses a specific question. Over time, the influence of this work extended into practical applications. The idea that moving charges create magnetic fields is at the heart of many technologies. Generators convert mechanical motion into electrical energy by using magnetic effects. Motors use magnetic fields to produce motion. These devices rely on the same principles demonstrated by the rotating disk. Yet, despite its practical importance, the true value of the experiment lies in its contribution to knowledge. It answered a fundamental question about the nature of forces. It showed that motion and magnetism are inseparably linked. And it did so in a way that was clear, precise, and convincing. Looking back, it is easy to see the rotating disk experiment as a natural step in the development of physics. But at the time, it required insight, creativity, and determination. It required a willingness to explore new ideas and to test them with care and precision. In the end, this phase of the story is about confirmation and confidence. It is about taking an idea and proving it beyond doubt. It is about showing that the universe operates according to consistent and discoverable laws. The rotating disk continued to spin, but its significance reached far beyond the laboratory. It became a symbol of how science progresses from question to hypothesis, from experiment to evidence, and from uncertainty to understanding. Imagine reaching a point in scientific discovery where a bold idea is no longer just a possibility, but a proven reality. After careful experiments and precise measurements, a powerful truth begins to emerge. Electricity in motion creates magnetism. This is not a guess, not a theory waiting for confirmation. It is a principle grounded in observation, one that reshapes how we understand the forces of nature. At first glance, the idea may seem simple. When electric charges move, they produce a magnetic field. But beneath this simplicity lies a profound shift in perspective. It means that magnetism is not a separate, independent force. Instead, it is a direct consequence of motion, specifically, the motion of electric charge. To understand why this matters, we must go back to how scientists originally viewed electricity and magnetism. For a long time, they were treated as distinct phenomena. Electricity was associated with charges, sparks, and currents. Magnetism was associated with magnets, compasses, and invisible forces acting at a distance. While experiments hinted at a connection, the true relationship remained unclear. The realization that motion links these two forces changed everything. It provided a unifying idea. Whenever electric charges move, they generate magnetic effects. This means that magnetism is not something separate. It is simply another way in which electric charges interact with the world when they are in motion. This insight is at the heart of electromagnetism, a field that brings together electricity and magnetism into a single framework. Within this framework, electric fields and magnetic fields are not isolated. They are deeply interconnected, constantly influencing each other in ways that depend on motion and change. To make this idea clearer, imagine a single electric charge. When it is at rest, it creates an electric field around it. This field can push or pull other charges, but it does not produce magnetism. Now imagine that the same charge begins to move. The moment it starts moving, something new appears: a magnetic field. This magnetic field is not an added feature or an external effect. It is a natural result of the charge's motion. The faster the charge moves, the stronger the magnetic effect becomes. If many charges move together, their combined motion creates a larger magnetic field. This relationship between motion and magnetism can be seen in many everyday situations. When electric current flows through a wire, the moving electrons produce a magnetic field around the wire. This is why a current-carrying wire can influence a nearby compass needle. The compass is not responding to the wire itself, but to the magnetic field created by the moving charges inside it. But the principle goes far beyond simple circuits. It applies to all forms of moving charge, whether in straight lines, circles, or more complex paths. Even in cases where there is no visible current, as long as charges are in motion, magnetism will be present. One of the most important aspects of this idea is its universality. It does not depend on the type of material, the shape of the system, or the scale of the motion. Whether we are dealing with tiny particles or large electrical systems, the same rule applies. Moving charges create magnetic fields. This universality gives the principle a powerful predictive ability. Scientists can analyze a system, determine how charges are moving, and predict the magnetic effects that will result. This ability to predict and explain behavior is one of the key goals of physics. The connection between motion and magnetism also helps explain the behavior of permanent magnets. At first, a magnet may seem like a completely different kind of object, something that produces a magnetic field without any visible motion. But at a deeper level, the same principle applies. Inside a magnet, electrons are constantly moving. They spin and orbit within atoms, creating tiny loops of current. These microscopic motions combine to produce the overall magnetic field of the magnet. So even in a permanent magnet, magnetism arises from motion, just at a scale too small to see directly. This idea reveals a hidden layer of reality. It shows that what appears static on the surface may actually involve dynamic processes at a deeper level. It reminds us that the true nature of physical phenomena often lies beneath what we can observe directly. The concept that moving charges create magnetism also leads to important questions about energy and interaction. When a charge moves and produces a magnetic field, where does that energy come from? How does the magnetic field influence other charges and currents? These questions open the door to a deeper understanding of how forces operate. The answers lie in the interaction between electric and magnetic fields. These fields can store and transfer energy. They can influence the motion of charges, which in turn can change the fields. This continuous interaction creates a dynamic system in which motion and force are closely linked. The theoretical foundation for this understanding was developed by scientists such as James Clerk Maxwell. His equations describe how electric and magnetic fields are generated and how they interact. They show that a moving charge produces a magnetic field, and that changing fields can influence each other in complex ways. Maxwell's work provided the mathematical framework, but it is the principle itself, the idea that motion creates magnetism, that gives the theory its physical meaning. It connects the equations to real-world behavior, making it possible to apply them to practical situations. One of the most striking consequences of this principle is its role in the generation of electromagnetic waves. When charges accelerate, meaning their motion changes, they produce changing electric and magnetic fields. These changing fields can propagate through space as waves, what we know as light. This means that light itself is a result of moving charges and the fields they create. It is not a separate phenomenon, but a direct extension of the same principles that govern electricity and magnetism. This connection unifies different areas of physics into a single, coherent picture. The idea that electricity in motion creates magnetism also has practical implications. It forms the basis of many technologies that we rely on every day. Electric motors use magnetic fields produced by currents to create motion. Generators use motion to produce electric currents through magnetic effects. Transformers, communication systems, and countless other devices operate based on these principles. Yet, beyond its applications, the true importance of this idea lies in what it reveals about the nature of the universe. It shows that forces are not isolated or independent. They are connected, influenced by motion, and governed by consistent laws. It also highlights the role of observation and experimentation in science. The principle was not accepted simply because it made sense. It was confirmed through careful measurement and repeated testing. This process of verification is what gives scientific knowledge its strength. Another important aspect is the shift in perspective it requires. Instead of thinking of magnetism as something separate, we begin to see it as part of a larger system. We start to understand that what we observe depends on motion, context, and interaction. This shift has far-reaching implications. It encourages us to look for connections between different phenomena, to seek underlying principles that unify our understanding. It shows that simplicity and complexity can coexist, that a simple idea can explain a wide range of behaviors. As the understanding of this principle deepened, it became a cornerstone of modern physics. It influenced not only electromagnetism, but also later developments in relativity and quantum theory. The idea that motion affects how forces appear would eventually lead to even more profound insights about space and time. But even without going that far, the core idea remains powerful on its own. Moving charges create magnetic fields. This simple statement captures a fundamental truth about the universe. It connects motion to force, electricity to magnetism, and theory to reality. It is a reminder that the laws of nature are often elegant in their simplicity, yet vast in their implications. From the smallest particles to the largest systems, the same principles apply, guiding the behavior of everything around us. And so, what began as a question whether motion could create magnetism becomes a foundational concept. A concept that not only answers the question, but opens the door to a deeper understanding of the world. As this understanding matured, the idea that moving charges create magnetism began to reveal layers of meaning that went far beyond a single principle. It was no longer just a statement about what happens when charges move. It became a framework for interpreting a wide range of physical phenomena, from simple circuits to the behavior of matter itself. One of the most important developments at this stage was the realization that electric and magnetic effects are not fixed properties, but depend on motion and perspective. This means that what one observer measures as a purely electric effect, another observer, moving differently, might interpret as a combination of electric and magnetic effects. This insight pushed physics into a more dynamic and relational way of thinking. To understand this, imagine observing a stream of moving charges from different points of view. If you are stationary relative to the charges, you may only detect an electric field. But if you move alongside or past those charges, their motion relative to you changes, and a magnetic effect becomes noticeable. This does not mean that the laws of physics are changing. It means that electric and magnetic fields are two aspects of the same reality, revealed differently depending on motion. This deeper viewpoint strengthened the unity of electromagnetism. It showed that electricity and magnetism are not just connected, they are inseparable. They form a single, coherent system in which motion plays a central role. This realization would later become essential in the development of modern theories of space and time. Another important consequence was the refinement of how scientists describe currents. Earlier, current was often imagined as something confined to wires, a flow from one point to another. But with the understanding that any moving charge produces magnetism, the concept of current expanded. A rotating system, oscillating charges, or even microscopic movements inside atoms could all be understood as forms of current. This broader definition allowed scientists to analyze more complex systems. For example, in conductive materials, electrons move in response to electric fields, creating currents and magnetic effects. In insulating materials, charges may not flow freely, but they can still shift or rotate, producing subtle magnetic influences. Even in empty space, moving charged particles, such as those in cosmic radiation, generate magnetic fields. The idea also deepened our understanding of how forces act between moving charges. When charges are in motion, they not only create magnetic fields, but also experience forces due to those fields. These forces depend on the direction and speed of motion, leading to rich and sometimes surprising behavior. For instance, two parallel currents flowing in the same direction attract each other, while currents in opposite directions repel. This behavior can be explained entirely through the magnetic fields created by the moving charges. What might seem like a new type of force is actually a natural consequence of the same underlying principle. This interconnected behavior highlights the elegance of physical laws. A single idea motion of charge produces magnetism, can explain a wide range of effects that might otherwise seem unrelated. It reduces complexity by revealing the common thread that runs through different phenomena. The influence of this principle also extended into the microscopic world. Inside atoms, electrons are not stationary. They move in orbit, like patterns, and possess intrinsic motion known as spin. These movements generate tiny magnetic fields, which combine to determine the magnetic properties of materials. In some materials, these microscopic magnetic effects cancel out, resulting in no overall magnetism. In others, they align in such a way that a strong magnetic field is produced. This explains why some substances become magnets while others do not. Once again, motion at a fundamental level is the key. The connection between motion and magnetism also plays a crucial role in energy transfer. When charges move and create magnetic fields, they store energy in those fields. This energy can then be transferred, transformed, or used to perform work. This is the basis for many electrical technologies. Generators, for example, convert mechanical motion into electrical energy by exploiting magnetic effects. When a conductor moves through a magnetic field, or when a magnetic field changes around a conductor, charges are set into motion, creating current. This is essentially the reverse process motion, creating electricity through magnetism, which itself originates from moving charges. Motors operate on the same principle, but in reverse. Electric currents create magnetic fields, and these fields exert forces that produce motion. This continuous interaction between motion, electricity, and magnetism forms the backbone of modern electrical systems. The theoretical understanding of these processes was greatly influenced by James Clerk Maxwell. His equations unified the behavior of electric and magnetic fields and showed how they evolve over time. They provided a mathematical description of the very principle being explored, that moving charges give rise to magnetic effects. Maxwell's work also revealed that changing electric and magnetic fields can sustain each other, leading to the propagation of electromagnetic waves. This discovery connected the motion of charges to the transmission of energy through space, further expanding the significance of the principle. As the concept became fully integrated into physics, it began to influence how scientists approached new problems. Instead of treating phenomena as isolated, they looked for underlying motion and interaction. They asked how charges were moving, how fields were changing, and how these factors combined to produce observable effects. This approach proved to be incredibly powerful. It allowed scientists to predict new phenomena, design experiments, and develop technologies with a high degree of confidence. It also provided a framework for understanding complex systems, from electrical circuits to astrophysical processes. The principle also encouraged a deeper appreciation for the role of measurement and observation. Detecting magnetic effects often requires sensitive instruments and careful interpretation. The ability to measure small changes in fields and currents became essential for advancing knowledge. Over time, this led to the development of more sophisticated hypothetical and techniques, enabling scientists to explore phenomena at smaller scales and higher precision. Each improvement in measurement opened the door to new discoveries, reinforcing the importance of the original insight. Beyond its scientific and technological impact, the idea that moving charges create magnetism carries a philosophical significance. It shows that the properties of nature are not always fixed. They can depend on motion and interaction. It challenges us to think beyond static descriptions and to consider the dynamic relationships that shape reality. It also illustrates the power of unification in science. By linking electricity and magnetism through motion, a wide range of phenomena can be understood within a single framework. This unification simplifies our understanding while expanding its scope. As this phase of understanding reached completion, the principle stood as one of the cornerstones of physics. It had been tested, confirmed, and applied in countless ways. It provided both explanation and prediction, connecting theory with experiment and observation with application. What began as a question about moving charge had evolved into a comprehensive understanding of how motion generates magnetic effects. It revealed the hidden connections between forces, showed the importance of perspective, and demonstrated the consistency of natural laws. And perhaps most importantly, it reminded us that even the simplest ideas can have profound implications. A moving charge may seem like a small thing, but from it emerges a fundamental force, one that shapes the behavior of matter, enables modern technology, and deepens our understanding of the universe. Imagine trying to detect something so small that it almost doesn't exist, at least not in any obvious way. This was the challenge scientists faced when they attempted to prove that moving electric charges create magnetism. The idea itself was powerful, but without precise measurement, it would remain nothing more than a theory. This is where the importance of accuracy, instruments, and scientific discipline comes into focus. At this stage, the story is no longer just about discovery, it is about proof. In science, proof does not come from belief or assumption, it comes from measurement. And when the effect you are trying to measure is extremely weak, the quality of your tools and methods becomes everything. When Henry Augustus Rowland conducted his rotating disk experiment, he was not working with strong, easily detectable magnetic fields. The magnetic effect produced by the moving charges on the disk was incredibly small, far weaker than the magnetic field of a simple current, carrying wire. Detecting it required instruments of exceptional sensitivity. This is where precision becomes the hero of the story. Rowland used highly refined ubiquita and is capable of detecting even the slightest deflection caused by a magnetic field. These instruments were designed to respond to minute changes, allowing him to observe effects that would otherwise be invisible. But having sensitive instruments is only part of the solution. The environment in which the experiment is conducted must also be carefully controlled. Magnetic fields exist all around us. The Earth itself produces a magnetic field, and nearby objects, especially those made of metal, can interfere with measurements. Even small vibrations or temperature changes can affect the results. Rowland understood that to prove his idea, he needed to eliminate as many sources of error as possible. He carefully isolated his experiment from external influences. He ensured that the disk was balanced and rotated smoothly. He controlled the distribution of charge on the disk so that it would behave predictably. Every detail was considered, because even a tiny mistake could lead to incorrect conclusions. This level of care highlights an essential principle of science. Accuracy is not accidental. It is achieved through careful planning, repeated testing, and constant attention to detail. Precision is not just about having good tools. It is about using them correctly and understanding their limitations. Another key aspect of precision measurement is repeatability. A single observation is never enough to establish a scientific fact. The experiment must be repeated, and the same result must appear each time. Rowland performed his experiment multiple times, adjusting conditions and verifying that the magnetic effect consistently matched theoretical predictions. This consistency is what transforms an observation into evidence. When results are repeatable, they gain credibility. Other scientists can perform the same experiment and obtain the same outcome, strengthening confidence in the conclusion. The relationship between theory and measurement also plays a crucial role here. Theoretical work, especially that of James Clerk Maxwell, had already predicted that moving charges should produce magnetic fields. But theory alone is not enough. It must be tested against reality. Rowland's measurements provided that test. Not only did he detect a magnetic field, but the strength and direction of the field matched what theory predicted. This agreement between theory and experiment is one of the strongest forms of validation in science. It shows that our mathematical descriptions of nature are accurate reflections of physical behavior. Precision measurement also helps distinguish between real effects and noise. In any experiment, there are always unwanted signals, random fluctuations, environmental disturbances, or instrument limitations. The challenge is to separate these from the actual phenomenon being studied. Rowland achieved this by carefully analyzing his data and ensuring that the observed magnetic effect was not due to random variation. He compared results under different conditions, checked for consistency, and ruled out alternative explanations. This process of elimination is a critical part of scientific reasoning. Another important lesson from this stage is the role of innovation. Detecting such a weak magnetic field required not only existing tools, but also improvements and creative approaches. Scientists often need to design new methods or refine existing ones to reach higher levels of precision. This spirit of innovation continues in modern science. As we explore smaller particles and weaker forces, the demand for precision becomes even greater. Advanced hypotheses, such as particle detectors and quantum sensors, are built on the same principle: the need to measure the nearly unmeasurable. The rotating disk experiment also shows that precision is not just about numbers. It is about trust. When an experiment is conducted with care and accuracy, its results become reliable. This reliability allows other scientists to build on those findings, creating a chain of knowledge that grows over time. Without precision, this chain would break. Errors would accumulate, and conclusions would become uncertain. But with precise measurement, each discovery becomes a solid foundation for the next. This stage of the story teaches us that science is not only about big ideas. It is also about the discipline required to test those ideas. It is about patience, attention to detail, and a commitment to accuracy. These qualities are just as important as creativity and insight. It also reminds us that nature often reveals its secrets in subtle ways. The most important truths are not always the most obvious. Sometimes they are hidden in small effects that require careful observation to uncover. In the end, the success of this experiment was not just due to the concept of moving charges creating magnetism. It was due to the ability to measure that effect with precision and confidence. It turned an invisible phenomenon into a measurable reality. And that is the true power of scientific proof. It takes an idea and anchors it in evidence. It transforms uncertainty into understanding. And it shows that with the right tools and methods, even the smallest effects can lead to the greatest discoveries. At this stage of the journey, the focus shifts from a single experiment to a much larger framework, one that connects individual discoveries into a unified understanding of nature. The idea that moving charges create magnetism does not stand alone. It fits into a broader system of laws that describe how electric and magnetic fields behave, interact, and evolve. This system is most powerfully expressed through the work of James Clerk Maxwell. Before Maxwell, scientists had already discovered many separate facts about electricity and magnetism. They knew that electric charges exert forces, that currents produce magnetic fields, and that changing magnetic fields can induce electric currents. But these ideas were scattered, like pieces of a puzzle without a clear picture. Maxwell's great achievement was to bring all these pieces together into a single, coherent theory within electromagnetism. He developed a set of equations that describe how electric and magnetic fields are generated and how they influence each other. These equations did not just summarize known results, they predicted new ones. One of the key insights from Maxwell's work is that electric and magnetic fields are deeply interconnected. A moving electric charge creates a magnetic field, and a changing magnetic field can create an electric field. This mutual relationship means that electricity and magnetism are not separate forces, but different aspects of the same phenomenon. The rotating disk experiment provided strong experimental support for this idea. By showing that motion of charge produces magnetism even without a traditional current, it confirmed a fundamental part of Maxwell's theory. It demonstrated that the equations were not just mathematical abstractions, they described real physical behavior. To understand this connection more clearly, consider what Maxwell's theory says about moving charges. According to his equations, any motion of electric charge should generate a magnetic field. This prediction applies universally, whether the charge moves in a straight line, in a loop, or on the surface of a rotating object. When experiments like the rotating disk confirmed this prediction, they strengthened confidence in the entire theoretical framework. This is important because a theory in physics is not judged by one result alone. It must consistently match observations across many different situations. Each successful experiment adds another layer of support. Another profound outcome of Maxwell's theory is the prediction of electromagnetic waves. When electric and magnetic fields change over time, they can propagate through space as waves. These waves travel at the speed of light, leading to the realization that light itself is an electromagnetic phenomenon. This connection is extraordinary. It means that the same principles governing moving charges and magnetic fields also explain how light travels. The rotating disk experiment, by confirming one part of this framework, indirectly supports this much larger picture. The relationship between experiment and theory here is essential. Theory provides a set of predictions, while experiment tests those predictions. When the two agree, our understanding becomes more complete. When they do not, it signals that something needs to be revised. In this case, the agreement was strong, reinforcing the validity of Maxwell's ideas. The rotating disk experiment also helped clarify the concept of current in Maxwell's equations. It showed that current is not limited to charges moving through wires. Any motion of charge can be treated as a form of current, contributing to the magnetic field. This broader definition makes the theory more flexible and widely applicable. This flexibility is one of the strengths of Maxwell's framework. It allows scientists to analyze a wide range of systems using the same basic principles. Whether studying electrical circuits, magnetic materials, or electromagnetic waves, the same equations apply. Another important aspect is the predictive power of the theory. Once the relationship between motion and magnetism is established, scientists can calculate the magnetic field produced by any moving charge distribution. This ability to predict behavior before observing it is one of the hallmarks of a successful scientific theory. The rotating disk experiment played a crucial role in building this predictive confidence. It showed that even in a non-traditional setup, the theory holds true. This kind of confirmation is especially valuable because it tests the theory in new and challenging conditions. It also highlights the unity of physical laws. The same principles that explain simple experiments also apply to complex systems. This unity suggests that the laws of nature are consistent and universal, not limited to specific cases. As the connection between experiment and theory became clearer, it influenced the direction of future research. Scientists began to explore more complex interactions between electric and magnetic fields, leading to new discoveries and applications. The foundation provided by Maxwell's theory, supported by experiments like the rotating disk, made these advances possible. The impact of this connection extends beyond physics itself. It has practical implications in engineering, communication, and technology. Devices such as radios, televisions, and wireless communication systems all rely on electromagnetic waves, which are described by Maxwell's equations. But beyond applications, there is a deeper significance. The agreement between experiment and theory shows that the universe operates according to consistent principles that can be discovered and understood. It demonstrates the power of human reasoning combined with observation. It also reveals the beauty of scientific understanding. A single set of equations can describe a vast range of phenomena, from the motion of charges to the propagation of light. This simplicity and elegance are part of what makes physics so compelling. In the end, the connection to Maxwell's theory transforms the rotating disk experiment from an isolated result into part of a grand structure. It shows how individual discoveries contribute to a larger understanding. It links observation to theory and theory to reality. This stage of the story is about unity and confirmation. It shows that the principle of moving charges creating magnetism is not just an isolated fact, but a key part of a comprehensive framework that explains how the physical world works. By this stage, the discovery has moved far beyond the laboratory. What began as a careful experiment proving that moving charges create magnetism now becomes something much larger, something that shapes the modern world. The true power of this idea is revealed in its impact on both physics and technology, influencing how we understand nature and how we build the systems around us. At its core, the principle is simple. When electric charges move, they produce magnetic fields. But this simple rule is the foundation of countless devices and innovations that define modern life. It is not an exaggeration to say that much of today's technology depends directly on this idea. Consider one of the most important inventions in human history, the electric generator. A generator converts mechanical motion into electrical energy. It works because motion in a magnetic field causes charges to move, creating current. But this process also depends on the reverse idea. Moving charges produce magnetic effects, and changing magnetic fields influence charges. This interplay is rooted in the same principles explored within electromagnetism. Electric motors operate on a closely related concept. Instead of converting motion into electricity, they convert electrical energy into motion. When current flows through coils of wire, the moving charges create magnetic fields. These fields interact with other magnetic fields, producing forces that cause parts of the motor to move. Every fan, pump, or electric vehicle relies on this principle in some form. The importance of this idea extends into communication technology as well. Radios, televisions, and wireless systems all depend on electromagnetic waves. These waves are produced by accelerating charges, which create changing electric and magnetic fields that travel through space. The same fundamental concept, motion of charge leading to magnetic effects, lies at the heart of how information is transmitted across distances. Even the devices we use every day, such as smartphones and computers, rely on these principles. Inside these devices, tiny electric currents flow through circuits, creating magnetic fields and interacting with other components. Data storage technologies, such as hard drives, use magnetic properties that ultimately depend on the motion of charges at microscopic levels. Beyond practical applications, this principle has had a profound impact on the development of physics itself. It helped unify different areas of study and provided a foundation for further discoveries. The work of James Clerk Maxwell built on this idea, leading to a complete theory of electromagnetic fields. Later, this understanding influenced the development of relativity and quantum mechanics, showing how deeply connected these concepts are. One of the most important contributions of this discovery is the way it changed how scientists think about forces. Instead of viewing electricity and magnetism as separate, they are now seen as parts of a single, unified system. This shift in perspective has guided research for generations, encouraging scientists to look for deeper connections between different phenomena. The impact is also visible in how we study materials. Magnetic properties of substances, whether they are strongly magnetic, weakly magnetic, or not magnetic at all, can be explained by the motion of electrons within atoms. This understanding has led to the development of new materials with specific properties, used in electronics, energy systems, and medical technology. In medicine, for example, technologies like MRI scanners rely on magnetic fields to create detailed images of the human body. These magnetic fields are generated and controlled using the same principles of moving charges and electromagnetism. Without this foundational understanding, such advanced diagnostic tools would not exist. The influence of this idea also extends into energy systems. Modern power grids depend on the generation, transmission, and use of electrical energy, all of which involve moving charges and magnetic effects. Transformers, which adjust voltage levels for efficient transmission, operate based on changing magnetic fields and induced currents. What makes this impact so remarkable is its universality. The same principle applies whether we are dealing with large power stations or tiny electronic circuits. It connects different scales and systems, showing that the laws of physics operate consistently everywhere. Another important aspect is the role this discovery plays in innovation. By understanding how moving charges create magnetic fields, engineers and scientists can design new devices and improve existing ones. This knowledge allows for creativity within a framework of reliable laws, leading to continuous technological advancement. At the same time, the impact is not only practical, but also intellectual. It deepens our understanding of the universe. It shows that complex systems can be explained by simple principles, and that these principles can be tested and confirmed through experiment. The rotating disk experiment, which helped demonstrate this idea, may seem small compared to modern technologies, but its significance lies in what it revealed. It provided clear evidence for a fundamental rule that governs a vast range of phenomena. It turned an abstract concept into a proven fact. This connection between simple experiments and large-scale impact is a common theme in science. Many of the technologies we rely on today are built on discoveries that once seemed purely theoretical. It is a reminder that understanding nature at a fundamental level often leads to practical benefits in ways that are not immediately obvious. The legacy of this principle continues to grow. As new technologies emerge, such as renewable energy systems, advanced electronics, and communication networks, they all depend on the same underlying ideas. The motion of charges and the magnetic effects they produce remain central to innovation. In the end, this stage of the story is about transformation. A single scientific insight evolves into a cornerstone of modern life. It shapes not only our understanding of physics, but also the tools and systems that define our world. What began as a question about moving charges becomes a driving force behind technological progress. It connects theory to application, experiment to invention, and knowledge to everyday experience. And it shows that even the most fundamental discoveries can have far-reaching consequences, influencing both how we think and how we live. At this final stage, the focus turns to legacy, the lasting impact of a discovery that began with a simple question and a carefully designed experiment. What Henry Augustus Rowland achieved was not just a confirmation of a scientific idea, but the creation of a foundation that continues to influence physics, technology, and the way we approach knowledge itself. Legacy in science is not measured only by what is discovered, but by what that discovery makes possible. Rowland's work proved that motion of electric charge produces magnetism, and in doing so, it helped solidify one of the central principles of electromagnetism. This principle did not remain confined to textbooks or laboratories. It became a building block for future generations of scientists and engineers. One of the most important aspects of Rowland's legacy is the way his experiment strengthened the connection between theory and evidence. At a time when ideas about electricity and magnetism were still being unified, his work provided clear experimental confirmation. It showed that theoretical predictions, especially those associated with James Clerk Maxwell, accurately described real physical behavior. This connection between theory and experiment is one of the defining features of modern science. Rowland's work demonstrated that even the most abstract ideas can, and must, be tested. It reinforced the idea that scientific knowledge is built on evidence, not assumption. This approach continues to guide research in every field of science today. Another important part of his legacy is the emphasis on precision. The rotating disk experiment required extraordinary accuracy to detect extremely small magnetic effects. This level of care set a standard for experimental physics. It showed that even subtle phenomena can be studied and understood if the right methods and tools are used. This influence can be seen in modern scientific research, where precision measurement plays a crucial role. From particle physics to space exploration, scientists rely on highly sensitive instruments to observe and analyze the smallest details. The mindset that Rowland exemplified careful design, attention to detail, and commitment to accuracy remains essential. Rowland's discovery also contributed to a broader shift in how scientists think about forces and interactions. By showing that magnetism arises from moving charges, his work helped unify different areas of physics. It encouraged researchers to look for underlying connections rather than treating phenomena as separate and unrelated. This spirit of unification has driven many of the greatest advances in science. It led to the development of comprehensive theories that explain a wide range of phenomena using a small set of principles. In this sense, Rowland's work is part of a larger movement toward understanding the universe as a coherent and interconnected system. The technological impact of his legacy is equally significant. The principle he helped confirm is at the heart of modern electrical and electronic systems. From power generation to communication networks, the idea that moving charges create magnetic fields is used in countless applications. However, the true legacy goes beyond specific devices or technologies. It lies in the way this discovery has shaped human understanding. It has changed how we think about motion, force, and interaction. It has shown that even invisible phenomena like electric and magnetic fields can be studied with clarity and precision. Rowland's work also serves as an example of the power of curiosity-driven research. He was not trying to invent a new machine or solve a practical problem. He was exploring a fundamental question about nature, yet the answer to that question turned out to have far-reaching consequences. This highlights an important lesson. Basic research often leads to unexpected applications. By seeking to understand the underlying principles of the universe, scientists create knowledge that can later be used in ways that were not originally imagined. Another lasting aspect of Rowland's legacy is the inspiration it provides. His experiment shows that significant discoveries do not always require complex or large-scale setups. What matters is the clarity of the question, the creativity of the approach, and the precision of the execution. For students and young scientists, this is a powerful message. It shows that careful thinking and dedication can lead to meaningful contributions, even in areas that seem well understood. It encourages a mindset of exploration and persistence. The rotating disk itself has become a symbol of this legacy. It represents the moment when an abstract idea was turned into measurable reality. It stands as a reminder that science progresses through a combination of theory, experiment, and verification. As time has passed, the principles confirmed by Rowland have been extended and refined. They have been incorporated into more advanced theories and applied in new contexts. Yet, the core idea remains the same. Moving charges create magnetic fields. This simple statement continues to guide our understanding and innovation. The legacy also extends into education. The experiment and its results are taught as part of the foundation of physics. They help students understand the connection between concepts and real-world behavior. They illustrate how scientific knowledge is built step by step. In a broader sense, Rowland's work contributes to humanity's collective knowledge. It is part of the ongoing effort to understand the laws that govern the universe. Each discovery adds to this understanding, creating a more complete picture of reality. In conclusion, the legacy of Rowland's discovery is both deep and wide. It strengthened the foundations of electromagnetism, influenced the development of modern physics, and enabled countless technological advances. It demonstrated the importance of precision, the power of experimentation, and the value of connecting theory with evidence. Most importantly, it showed that even a simple experiment can have a lasting impact. By revealing a fundamental truth about the relationship between motion and magnetism, Rowland helped shape the course of science. His work continues to resonate, reminding us that the pursuit of knowledge is a journey that extends far beyond any single discovery.